Hello everyone. So in this subject partial differential equations, today we will discuss about general nonlinear equations. It comes under section 2.9 of the text, an introduction to partial differential equations. So we will see the general nonlinear equations, how to solve the general nonlinear equation. So this is a general form of a nonlinear equation. So it is f of x, y, u, ux, uy equal to 0. Here u is a function of x and y. Suppose we denote ux by p and uy by q. Now I can write this as f of x, y, u, p, q equal to 0. Now we will see how to solve such nonlinear equations. Now, to ensure that the equation 1 consists of first order equations, we must have the non-degeneracy condition. So, non-degeneracy condition says that fp square plus fq square should not be equal to 0. So what happens if this is equal to 0? If it is equal to 0, then both fp and fq must be 0. So fp must be 0 and fq must be 0. It means that the partial derivatives with respect to p and q are 0, and hence the order is again 0th order. It is not a first order. So to ensure that one contains a first order PD, we must have that both fp and fq, that is both derivatives, should not vanish simultaneously. So this is the non-degeneracy condition. Now we take a point x naught, y naught, u naught. Let it be a fixed point on the surface. Then we have the equation f of x naught, y naught, u naught, p, q equal to 0. Now you can see that this is an implicit relation containing p and q. So from this relation and using implicit function theorem, we can write q as a function of p. So it means that q and p are not independent. So q can be written as a function of p. So this can be written as f of x naught, y naught, u naught, p, some f of p equal to 0. So we see that as p varies, this represents a one parameter family. So this represent a one parameter family, and since there is only one parameter, p is that parameter. Now we will see the equation of tangent plane to the surface u equal to u of xy, passing through this point, passing through the point x naught, y naught, u naught, and it is orthogonal to p, q minus 1. So this is the normal vector. So the equation of the tangent plane passing through this point and which is orthogonal to pq minus 1. So since it is orthogonal to pq minus 1, we have the dot product of pq minus 1 dot x minus x naught, y minus y naught, u minus u naught should be equal to 0. Now this represents p into x. So this represents p into x minus x naught plus So we have the equation p into x minus x naught plus q into y minus y naught equal to u minus u naught. So this represents the equation of a tangent plane. And as p varies, this describes a one parameter family of planes through the point x naught, y naught, u naught. And these planes, as they have their envelope of these planes will be a surface, and that is called the envelope of these planes is called the Monge cone. It's called the so this spreads out this family, one parameter family of tangent plane spreads out a cone, and that cone is called the Monge cone. For example, you can see in this figure, this is one tangent plane. So this is the equation of a tangent plane. And this is another tangent plane. So this is the equation of a tangent plane. So these two are tangent plane. This green one and this blue one are the tangent plane. And you can see that this is a normal to this plane, and this is a Monge cone produced. So this is a Monge cone that we got from this family of, this is a one parameter family of tangent plane, and this will spread out a cone, and such cones are called the Monge cone. So now we will see So now we will see how we are generating the Monge cone from a family of tangent plane. For example, consider a one parameter family of spheres. Suppose I denote it by FA. So FA represent x minus. So we will see, so here the equation is x minus a whole square plus y square plus u square equal to 1. So here u usually represent the z axis. So it is just like x minus a whole square plus y square minus z square equal to 1. And we have to find the envelope of this one. This is a one parameter family because here a is a parameter. So the general method for finding the one parameter family is, we can write z as a function of z or u as a function of x, y, and we can write u as a function of x, y, and a, and we can write this as dou f by dou a of x, y, a equal to 0. That is, we have to differentiate this with respect to a, and we have to eliminate a. And we have to eliminate a. Suppose I am getting a as a function of x and y. So I get the equation f of so here we are getting like this. So f of xy, a of xy equal to 0. So in this way we can find the envelope of this one parameter family. So here it represents circles, family of circles. So this is having a as a center in the x-axis. So it is a0, 0 is a center. So u represent the z-axis. So here we have a, suppose this represent the x-axis. So here we have circles of this form. We are finding a one parameter family. So we have to write u as a function of x, y, a. We have to differentiate this with respect to a, and so solving these two equations, we will get a as a function of x and y. Substitute for a, so you will get f. So actually this is a surface, this is a surface. So when the intersection of two surfaces will be a curve. So two surfaces intersect in a curve, and when you take union of all these curves, we usually get the envelope. So in this case, we are getting, here we have a one parameter family of spheres in R3, and in this case, we are getting the envelope as a cylinder. So we are getting like this. So here you will get a cylinder of this form. So this is the envelope in this case. Okay. Now we will see what is the integral surface. How to get now from this, how to get our integral surface. How do we will define our integral surface? So for this, as in the case of quasi-linear PDE, what we did is we converted the partial differential equation to ordinary differential equation. We wrote the characteristic equation, and when we solved the characteristic equation, we got the characteristic curves. So here also we will follow the same, that is the method of characteristics. So here also we will see the method of characteristics. So it means that we should get a characteristic equation of the general form of our nonlinear PDE. So we have our equation, that is the equation of the tangent plane is x minus x naught p into. So we have the equation of the tangent plane is this